Okay, good morning, students. Today I want to explain about the logic gates. Okay, the realization of logic gates by using only NAND gates and NOR gates. Okay, so here you can see first logic gates. See the logic gates. Logic gates. The logic gates. You can see this is the first one is inverter, okay, or NOT gate. NOT gate. So NOT gate, if you see, so this is the symbol for NOT gate. We are giving A, Y equal to what? A bar. Okay. So what is the truth table? So A and Y. We are giving 0. We are getting 1. We are 1. We are giving 1. We are getting 0. Okay. This is about the NOT gate. And next you have AND gate. AND gate, if you see, this is the AND gate. A and B, the output is AB. Output is AB. So if you see the truth table, A, B, and Y. Okay. So that means if any of the input is 0, the output is 0. Okay. That is the definition in single line. Any of the input is 0, the output is 0. Otherwise, it is 1. Okay. And next, if you see the OR gate, see the OR gate. See the OR gate. OR gate. So this is the symbol for OR gate. A, B, and Y equal to what? A or B, and A, B, and the output is Y 0, 0, 0, 1, 1, 0, 1, 1. If any of the input is 1, the output is 1. Okay. If any of the input is 1, the output is 1. Okay. So this is the OR gate. Okay. Next. Second. Okay. Next, if you see, after OR gate, you have NAND gate. After OR gate, you have NAND gate. So this is a symbol for NAND gate. NAND gate. AB, and output is what? AB bar. AB bar. So if you see the truth, the inputs are A, B, and the output is Y. 4 possible combinations: 0, 1, 1, 0, 1, 1. Okay. So just opposite of this AND gate. So that means any of the input is 0, the output is 1, and otherwise the output is 0. Okay. This is the truth table for AND gate. Okay. And next, NOR gate. Okay. NOR gate. See the NOR gate. See the NOR gate. NOR gate. So symbol, if you see, this is the NOR gate. OR gate followed by an inverter. This is nothing but bubble. A and B. The output is A or B whole bar. Okay. If you see the truth table, this is A and this is B, and the output Y 0, 0, 0, 1, 1, 0, 1, 1. Okay. So just opposite of this OR gate is nothing but NOR gate. If any of the input is 1, the output is 0. And both inputs are 0 means the output is 1. Okay. So this is NOR gate. And next we have XNOR gate. XNOR gate. So XOR gate is also called as odd detector. Odd detector. So if there are odd number of ones, you are getting the output as 1. Okay. So this is output Y 0 0 0 1 1 0 1 1. So if any of the input is 1, the output is 1. Okay. And here it is 0. This is 0. So symbol for this one is so this is XOR gate. This is A and B, and Y equal to what? A XOR B. So this you can write as A bar B plus AB bar. A bar B plus AB bar. Okay, this is XOR gate. And next you have XNOR gate. You have XNOR gate. XNOR gate. XNOR gate. What is XNOR gate? So just opposite of that means XOR followed by an inverter is nothing but XNOR gate. We see the table. So A, B, and the output is Y 0 0 0 1 1 0 1 1. Okay. So this is also called as we can call as event detector. Event detector. So if any of the both inputs are same, even number of inputs are same, the output is 1. Otherwise, output is 0. Okay. And here if you see, this is the logic diagram for XOR gate. A and B, Y equal to what? A XNOR B. Okay. Here, so this dot will be there. Okay, this is the symbol. So what is the expression? AB or A bar B. Okay, AB or A bar B. Okay. So these are the logic gates. Next, I am going to implement these logic gates by using first NAND gate. Okay. So and also I'm implementing the logic expression by using NAND gate. Okay, by using only NAND gates. Okay. So this NAND gate and NOR gate are nothing but universal gates. Why? Because we can get any of the gate. We can implement any of the gate by using this NAND gate and NOR gate, or we can implement the combinational circuits by using this NAND gate and NOR gate. Okay. So first, I'm implementing NOT gate. Okay, I'm implementing NOT gate. So what is the symbol? This is the symbol for NOT gate. No? This is nothing but A and A bar. So this is equivalent to what? When inputs are tied together, so you are getting A. So Y equal to what? A and A whole bar. So from the AND law, you say you know that A and A equal to A. So this is A bar. Okay. And or one more thing you can do, like one input is A, another input is connected to logic 1. Logic 1. So what you are getting? So Y equal to A and 1 whole bar. This is equal to what? A bar. Okay. So this is how you can implement NOT gate by using only NAND gate. Okay, only NAND gate. And next AND gate. AND gate, how to implement? This is the logic symbol for AND gate. So this is A and this is B. So Y equal to what? AB. Y equal to AB. So first you take one NAND gate and this input is tied together and giving to one more NAND gate. This is A and this is B. Here we are getting AB bar. You know that AB bar whole bar, this is equal to what? AB. AB bar whole bar equal to AB. Okay, so this is the implementation of a AND gate by using NAND gate. Okay, and next, what is my next gate? Third gate, OR gate. Okay, so OR gate, if you see, so this is the symbol for OR gate. This is the symbol for OR gate. So this is A and this is B. Y equal to what? ARB. Okay, so how we can implement? Suppose if you write A bar and B bar whole bar. Okay, so this is equal to what? If you apply De Morgan's law, A bar whole bar or B bar whole bar, this is equal to ARB. Okay, so from this expression, I'm going to implement this OR gate. Okay, so how you can implement? So you take one input, an input tied together, and it is given to A. Okay, and another input, an input tied together, and it is given to B, and these inputs are given to one more NAND gate. Okay, so here this is A bar and this is nothing but B bar. So Y equal to what? A bar and B bar whole bar. So this is nothing but A bar whole bar. De Morgan's law I'm applying. Okay, B bar whole bar. So Y equal to what? ARB. Y equal to ARB. Okay, so this is the OR gate, implementation of OR gate by using the NAND gate. Anyway, next NAND gate is there. So we are implementing with the NAND gate itself. So what is the NAND gate? So this is the NAND gate. This is the NAND gate, A and B, and Y equal to what? AB whole bar. AB whole bar. Okay. Next, I want to implement the NOR gate. Okay. So NOR gate means from here itself you will get the NOR gate. Okay. OR gate, how I implemented? So NOR gate. So first you implement the OR gate by using the NAND gate. So this I implemented. So this is A and B. The output is given to one more NAND gate. Okay. Here what you are getting? ARB. Okay. These inputs are tied together and given to one more NAND gate. We are getting NOR gate. AB whole bar. Okay. AB whole bar. So like this you can implement a NOR gate. Okay. NOR gate. Okay. And next XOR gate, how to implement? So XOR gate, I need to implement XOR gate. Okay. So XOR operation by using NOR gate. XOR gate. XOR gate. So what is the symbol for XOR gate? This is the symbol for XOR gate. This is A, this is B, equal to what? A XOR B. A XOR B. So this is nothing but A bar B or AB bar. Okay, A bar B plus AB bar. So you implement like this XOR gate. So here A bar B plus AB bar. So one NAND gate, you take one NAND gate, you take one NAND gate. XOR gate by using NAND gate. So here this is A and this is A and this is B. So this is given to one more NAND gate. One more NAND gate. This is given to one more NAND gate. And these outputs are given to one more NAND gate. Okay. So here, what is this? This is nothing but AB bar, and this is A and AB bar whole bar. Okay. So AB bar equal to what? A bar or B bar. Okay. So this you can write as A and A bar or B bar whole bar. So if you multiply, so A and A bar or AB bar whole bar. So anyway, this is 0. So this is nothing but AB bar whole bar. Okay. Similarly, you will get here B and A bar or B bar whole bar. So this is nothing but A bar B or B bar and B. Okay. This is 0 whole bar. So this is nothing but A bar B whole bar. Okay. So this is given to this NAND gate AB bar and A bar B whole bar. So this is nothing but AB bar. Here whole bar is there. Okay. So AB bar whole bar plus A bar B whole bar whole. So A bar whole bar equal to A, no? So you are getting AB bar plus A bar B. A bar. Okay. So this is not how you are getting XOR gate. So how you get XNOR gate? This input you are giving to one more NAND gate input tied together. You are getting here. This is A XNOR bit. Okay. So here if you see AB bar or A bar B whole bar. Okay. So if you apply like De Morgan's law, so that means AB bar whole bar and A bar B whole bar. Okay, this is equal to what? A A bar or B bar whole bar and A bar or B bar, A bar whole bar or B bar. Okay, so this is equal to A bar or B or A or B bar. So if you multiply, what you are getting? A bar and A or AB or AB, A bar, B bar, B or B bar. So anyway, this is 0, this is 0. So what you are getting? AB or A bar, B bar. So this is nothing but AX not AX. Okay, like this, you need to implement whatever the gates and gate, not gate, and gate, or gate, and gate by using this uh, uh, by using. And next NOR gates, by using only NOR gate. If you see, so NOR gate, first NOT gate I am implementing. So you see, so this is A, this is A bar. Okay, so if I am implementing with this NOR gate, inputs are tied together, and so this is A or A whole bar. This is equal to A bar. Okay, this is NOR gate. And next, how to implement and NOT gate. Next, how to implement AND gate. Inputs are tied together, and here A, here B, Y equal to what? A, Y equal to A. Okay, this I want to implement. Okay, so how to implement? Let us take one NAND gate, one NOR gate. Here one more NOR gate, one more NOR gate. and here you take one more NOR. So this is A and this is B. This is A bar, B bar. So A bar or and get B bar whole bar equal to what? A bar whole bar and B bar whole bar. So complement of complement is nothing but 2 common. This is nothing but A. Okay. Normally with this expression you need to do. That is A bar or B bar whole bar. So if you apply De Morgan's law, A bar whole bar and B bar whole bar. So this is nothing but what? Okay. So this is AND gate, and then OR gate is simple. OR gate is simple. Just this is the symbol for OR gate. No, this is the symbol for OR gate. A and B. Y equal to what? A or B. Okay. So I need to implement the OR gate by using NOR gate. Okay. How to implement? So this is one NOR gate. So this is A and B. We are getting Y equal to what? A or B whole bar. This output is given to one more NOR gate. So what you are getting? So this is A or B whole bar whole bar. So this is equal to A or B. Okay. So this is OR gate. And next I need to implement NAND gate. Okay. So how you are getting NAND gate? From here itself you get the NAND gate. See here. This output is given to one more NOR gate. Inputs tied together. So this is AB whole bar. So this is nothing but NAND gate. NAND gate. Okay. And next, anyway, NOR gate is there. NOR gate is there. So we are implementing with the NOR gate itself. Okay, we are implementing with the NOR gate itself. So this is NOR gate. Implementing with the NOR gate itself. AB and Y equal to what? ARB whole bar. ARB whole bar. Okay. Just to respond, is it audible? Anyone? Respond. Join. So here, the next is XOR gate. XOR gate. Okay. So before that, I will implement XNOR gate. From that, you will get XOR gate. Okay. How to implement XNOR gate by using NAND and NOR gate. NOR gate. Okay. So here, we need to give one second. Here, one NAND gate. One NAND gate. So two inputs are there. Two inputs are there. And this input you take out. Okay. And given to one NOR gate. And one more input to take out. Okay. And this is given to one more NOR gate, NOR gate. And this output is given to one more NOR gate. Okay. So here if you take, this is A and B, this is nothing but A or B whole bar. Okay. So this is nothing but A bar and B bar. So this is A or A bar, B bar, whole bar. Okay. So you know the absorption law, that is A or A bar B equal to what? A or B, no? So this is nothing but A or B bar whole bar. Okay. So A or B bar whole bar. Next, So next this one, B or A bar B bar. So this is nothing but B or A bar whole bar. Okay. So this is A bar or B. A bar or B. Okay. So if you give it to NOR gate, A or B bar whole bar or A bar or B whole bar whole bar. Okay. So this is nothing but what? This is nothing but A bar B bar whole bar or A bar whole bar B bar. Okay. Again whole bar. Okay. So this is A bar B or A B bar whole bar. Okay. So this is nothing but now what? XOR gate. Okay. Complement of XOR gate is nothing but what? XNOR gate. Okay. So complement of XOR gate is nothing but XNOR. Okay. Like this, you get the XNOR gate. And next, if you see this one, if you connect to one more NOR gate, tied together, y equal to what? So A XNOR B whole bar equal to what? A XOR B. So one of the interview question they can ask, how many NOR gates are required to implement the XNOR gate? So how many NOR gates are required? 5 NOR gates are required. How many NOR gates are required to implement XNOR gate? XOR gate, 5 NOR gates are required. And previously we have seen. Okay. In that NAND gate also, how many NAND gates are required to implement XOR gate means you have 4 NAND gates are required, and similarly, how many NAND gates are required to implement this XOR gate? This XNOR gate means 5 NOR gates are required. Okay, so this is about this one. Okay, implementation of NOR gate and NAND gate, logic gates by using NOR gate and NAND gate. Okay. So next, I need to implement the logic function by using NAND gate and NOR gate. Okay. So NAND gate and NOR gate. So here if you see, let us take the expression y equal to A bar B C bar. Okay. So before that, I will tell the steps. Step one. Uh, implement the Boolean expression using AOI logic. AOI logic is nothing but AND or invert logic. Okay, AND or invert logic. Step two. Apply bubble at output of AND gate and to input of OR gates. Okay, and next step three. Apply NOT gate. At places where bubbles are added. Okay. Step four. Look out for double inversion. Look out for double inversion. And cancel extra NOT gates. Cancel the extra NOT gates. NOT gates. Okay. And next, place the NAND equivalent. Okay. Step 5. Place the NAND equivalent. Okay. These are the steps. First, you need to implement the Boolean expression by using AND or invert logic. Apply the bubble at the output of AND gate and apply the bubble at the input of OR gate. So we already seen equivalency of the gate. That is NAND gate equal to what? NAND gate is equivalent to bubbled R. Okay. Based on that, you need to apply the output of the bubble at the output of AND gate. I need to apply the bubble at the input of OR gate. Okay. And next, apply NOT gate at the wherever you added the bubble, you need to add the NOT gates. Okay. And any two inverters are there, you need to cancel with each other. And at last, you need to place the NAND equal. Okay. So this is about the steps. First, you see. We'll see once. So I want to implement that is y equal to a bar or bc bar. Okay, this I need to implement. Okay, first you draw with AND or invert. Okay, AND or invert logic. Okay, so first this is inverter. Next you have one. So this is A, B, and C, and this output is given to one OR gate. Okay, so this is step 1. First, you need to draw given logic expression into AND or invert. Okay, step 2. What is step 2? You need to convert, means wherever the AND gates are there, you need to apply the bubble at the output, and wherever the OR gates are there, you need to add the bubble at the output. Okay, so here if you see, so this is AND gate. I'm adding the bubble at the output. So here this is A, B, and C, and here I'm adding the bubble at the input. I'm adding the bubble at the input, and this is output 1. Okay, and this is step 2. And step 3. So wherever you added the bubble, you need to add the inverter. So where you added the bubble, here you added the bubble, here you added the bubble, and here also you added the bubble. Okay, so wherever you added the bubble, you need to place the inverter. You need to add the inverters. Okay, so here if you see, that means this is the step 3. Step 3. If you see the step 3, here you added the bubble. So anyway, one inverter is there. So here you added the bubble. So you need to add inverter. And here if you see, so this is one AND gate. NAND gate, you added the bubble at the output. No? So this is anyway already there. A, B, and C. Okay. So this is given to bubbled NOR. Okay, and here you added the bubble. Need to add the inverter. Again, here also you added the bubble. Need to add the inverter. Okay, and next this is bubbled OR gate. Okay, and step 4. So if there is step 4, so if this is double inversion, you need to cancel each other. This is bubble inversion. You need to cancel each other. Okay, so that is step 4. Okay, so step 4, bubble inversion. You need to cancel and you need to redraw the circuit. So after redrawing, what I am getting, this is a NAND gate. So this is A, B, and C. So this is the one second. This is the bubbled NOR, no? Bubbled NOR. Okay, bubbled NOR. So this is the after cancelling the inverters, this is the circuit. Okay, bubbled NOR. Fifth step. So replace step 5. Replace all the equivalent NAND gates. Okay, so that means bubbled OR you can replace with the equivalent NAND gate. Okay, and here directly B is there, no? So here B is there directly. So this is A, and here B is there, and here this I can convert with an inverter, and this is one more NAND gate, and this is given to this NAND gate. So this is B and C. Okay. So next you need to verify either your answer is correct or not. Okay. So anyway, this is nothing but A, and here what is this? This is C bar, and this is nothing but BC bar, whole bar. Okay. So you can write this as B bar or C bar whole bar. So this is equal to what? B bar or C. Okay, B bar or C. So Y equal to what? Y equal to A and B bar or C whole bar. Okay. So if you apply this De Morgan's law, so this is A bar or B bar or C whole bar. Okay. So this is Y equal to what? A bar or B bar whole bar or C. So Y equal to A bar or B. Here we get C bar. Okay, B C bar. Okay. So I got the last expression. No? So whatever the expression is there, that I got. Okay. You can practice this one more implement by using NAND gate. You can practice this. Okay, with your own. So I'll draw the logic diagram. So the AOI to and or invert to NAND realization, NAND implementation. Okay, so NAND implementation. So I will draw the logic diagram so you can practice this. So just directly expression is not given, just need to draw the logic diagram. So from the logic diagram, you need to realize only by using NAND gates. Only by using NAND gates. Okay, second. So this logic diagram you need to implement only by using NAND gates. Okay, this is A, B, C, and D. Okay. So next, the same expression I need to implement by using NOR gates. Okay, by using NOR gates. First, I will tell the steps. Okay, implementation by using NOR gate. Implementation by using NOR gate. Okay, so if you see this one NOR gate, step one, implement the given Boolean expression. AOI logic. Okay. Implement given Boolean expression to AOI. AOI logic is nothing but and or invert logic. Okay. Step two, apply bubble at output of OR gate OR gate, and at input of AND gate. Input of AND gate. We know that NOR gate is equivalent to bubbled AND. On the De Morgan's law, you got no. So that is A or B whole bar equal to what? A bar and B bar. A bar and B bar. Okay. And next step 3. Step 3. Basically step 3. Apply NOT gate. Apply NOT gate. In the place of bubble, we have applied. Okay. In the place of bubble, we have applied. We have applied. Okay. Step 4. Step 4. Cancel NOT gates connected in series. Cancel NOT gates connected in series. Okay. Cancel NOT gates connected in series. Okay. And next step 6. Step 5. So place the NOT gate equivalent. Place the NOR gate equivalent. NOR gate equivalent. Okay. So these are the steps. First, you need to implement the given expression, Boolean expression into AND or invert logic, and apply. You need to apply the bubble at the output of OR gate, and you need to apply the bubble at the input of AND gate. Apply the NOT gate in place of bubble we have applied. Cancel NOT gate connected in series. Place the NOR gate equivalent. Okay. So we'll see the same example. So what example we have seen in the last by using NAND gates we have seen, no? In the color. Okay. So see here. So y equal to what? Y equal to A bar or BC bar. A bar or BC bar. So first you draw the logic diagram. So and or invert logic. Okay. This is A and this is B and this is C. Okay. And next here you will get OR gate. Okay. So this is OR gate. Okay. So this is step 1. Okay. Next step 2. What is step 2? You need to apply the bubble at the input of AND gate, and you need to add the bubble at the output of OR gate. Okay. So here this is an inverter. This is NAND gate. Okay. So you need to add the bubble at the output, and here you need to add the bubble at the input. 1 second. Here you need to add the bubble at the input of AND gate. Okay. AND gate. And here you need to add the bubble at the output of OR gate. Okay. You need to add the bubble at the output. Okay. Bubble at the output. Okay. And next, wherever you added the bubble, so step 3. Here I'm writing step 3. Wherever you added the bubble, you need to add the inverter. No? So where you added the bubble, so here anyway inverter is there. So this is A and B and C. Okay. So here you added the inverter, no? So you need to add the inverter wherever you added the bubble. So here you added the bubble. Okay, and here also one more inverter is there. So you need to add one more inverter, and where this is NAND gate. Okay, and next this is NOR gate. You added the bubble at the output, and here you need to add the inverter. Okay, so this is A, B, and C. So two inverters cancel each other, and last step. So you need to. So this is step 4. Step 4 means you need to cancel these wherever the inverters are in series. Okay. So step 4, if you draw. So step 4, if you draw, what you are getting? So this is an inverter, and this is an inverter. Here two inverters are cancelled. This is the bubbled and here this is OR with bubbled output we added, and this is an inverter output Y. So this is A, B, and C. Okay. So next step 5. Step 5. So you need to implement with only NOR gates. Okay. Here this is one NOR gate, and this is one NOR gate. This is one NOR gate, and bubbled and you can represent as NOR gate. Okay, and NOR gate, and here one more NOR gate, and here this is inputs tied together, and this is NOR. All are NOR gates only. So this is A, and this is B, and this is C. Okay. So this one is A bar, and this is B bar. Okay, and this is C. Okay. So here what you are getting? B bar or C whole bar. So this is B bar whole bar or C bar. So this is nothing but BC bar. BC bar. And anyway, this is A bar. Okay. So A bar or BC bar whole bar. So here you are getting A bar or BC bar whole bar whole bar. So you are getting your logic expression A bar or BC. A bar or BC. Okay. So our expression is verified. So what expression you took? This expression. So you got at last, you got this expression. Okay, this expression and this expression, both are same. Both are same. Okay, you can try with this same diagram, whatever I given. So you can implement with this one with only NOR gate. Okay, so now logic diagram is given. Okay, you can do as this as task. NOR implementation. NOR implementation. So how to implement? So this logic diagram is given. This you implement by using only NOR gate. This is the AND gate, and input is given to one OR gate, and this is output A, B, C, D. Okay, so this is so you can implement this one with the only NOR gates, and last you verify this. I think you understood. So first we have seen the logic gates. What are the logic gates? Like NOT gate, AND gate, OR gate, XOR gate, and XNOR gate. And that logic gates we implemented with the NAND, only NAND gate, and that logic gates we implemented only with the NOR gates. And next we have seen so that gates we have seen, and next we implemented this logic expression by using only NAND gates and NOR gates. We have seen the steps. So by following the steps, I implemented this with only NAND gates and NOR gates. Hope you understood. Okay, thank you.